Okay, so in the interest of time and in the interest of the time we have already lost, I can say that there is also a poster for what we are doing here and some to covering also all of this content that is in this presentation. So for more details, in particular on technical implementations and also more detailed screenshots and discussions, you're very much welcome also to drop by at the poster booth. This is work, and as I said, yeah, welcome. I'm very happy to present this work. That is together with, on one hand, people from FAIRmat, Shona Brockhauser, the entire B team from the infrastructure team, Markus Kühbach, Theodor Schang, and also people from Matwerk, and if you have Matwerk, a consortium here specifically, Tilman Hickel, Scharat, and Thomas Hammerschmidt, where we teamed up together in a project that was already from the proposal designed to bridge between the two consortia. And this has started, in fact, a year ago and is now slowly getting to speed, I would say. And in this sense, also, this is a little bit an update on what we are doing, also to show you how basically we can work together. And in fact, there are also collaborators we should mention here. This is the team from Lorenz Roman and Leoben, who have an Oasis running at the moment, who are also very early adopters and testers of this technology solutions that we're showing. Quickly on the field of atom probe tomography, it seems a little bit weird and always being bound to this microphone, but anyway, give it a try. Atom probe microscopy, as you can see, is a technique, physical technique whereby you have a small needle in the order of 20 to 100 nanometer, whereby you induce either voltage pulse or temperature pulse or laser pulse induced step-by-step operations of the atoms towards accelerating towards an electrode and then detect it. So basically, it's a coupling a mass time of flight result mass spectrometry with, in fact, a field effect microscope or field evaporation microscopy technique. And for that, you can basically nowadays with commercial instruments in a technique that is so-called atom probe tomography, reconstruct three-dimensionally, approximately at close to nanometer resolution, accurately the positions of atoms in a data set with detection efficiencies up to 80%, and data sets ranging in the size from a couple of million to, if you want to go crazy, 1 billion data sets. And the benefit is coupled to spatial information with the composition. When we talk about atom probe tomography and how it's done, it is strictly incorrect to just view this, and that's what, in fact, the experimentalists spend most time on, to just spend the time on a microscope. In fact, much is going before, much is happening after, to really arrive from the raw detector readings to actually the 1 or 2 figures that you typically have nowadays in material science and condensed matter physics paper, where you show the point cloud of atoms and all the structural features that by clustering together atoms into functional groups, or let's say interfaces and phase boundaries, from which you generate your knowledge. There's quite an involved process in that, including practical steps in the lab, as well as steps on the computer, computational steps, and nowadays more and more also these pieces of information are coupled with correlative microscopy and spectroscopy to really gain and somehow polish out these limitations that the techniques has with respect to spatial resolution. At some point, all of this ends in the paper, and the idea that I find particularly intriguing in this project, and why we designed it to really now set it up really from the start, or really walking through all these steps, is that we want at some point have the possibility to go back in these steps and not ask ourselves always, what have we done? We want to ideally have a system where we can basically find well-documented data artifacts along which we can have then breadcrumbs where we can follow up the trajectory and the time history of that project, so that we can learn, okay, what has happened, and ideally at some point also then share the data sets across the labs. And that's exactly what NOMAD Oasis is I think one of the most sophisticated solutions out there that at the moment couples these without me as a software developer having to implement this all from scratch. Let's go on a time axis a little bit to put you in perspective on what atom probe was about. And I jump, in fact, about a very, very long history, because it's important in this very small community. It's in fact 20 to 300 people worldwide who do this technique. It's key to understand that when we talk about now in this super hyper competitive field of research data management, every new research data management system popping up and like a mushroom farm, we have to understand that the process of getting there in atom probe tomography proceeds at a much slower speed. So here you see the first seminal experiments that Müller did in the 50s and 60s, where the first time actually saw atoms. And until then, it took almost 50, good to 50 years to get really commercial microscopes up where you could basically have a line, a Pearl chain of atoms, and at some point an area picture at 3 day. And already at that point in time, Miller came up with this approach. Okay, well, when you have the mass charge spectrum, which is not in fact a spectrum because you have no energy, you just have to count basically how many atoms are within a certain mass to charge state ratio window. Then you can say, okay, well, in this window, that's an atom, that's an aluminum atom, that's my iron atom. And that file format is basically still in existence in 2023. But the key problem with that file format is, and that's also where it comes really to documentation and reproducibility. The reproducibility is already lost here because you just say, okay, everything which is in between this window, that is iron, and what about the background correction? What about all the tweaks you do on our mass spectrum? That's typically lost, and that's why it has to be documented. But then this topic of FAIR and fair research and management got much traction, and already in 2014 and 15, Simon Ringer is on Professional Atom Probe Tomography in Sydney, brought this idea: why could we not build a shared research data infrastructure where people could upload data sets and atom probe data sets and share that? It was started, it stalled because limited support, limited funding, limited interest, primarily of the community. And then, however, people picked up this idea of fair openness, obviously because there was this whirlwind of activities following up. And then there was these like more comedies founded like in Gaithersburg in 2018, where in fact the community came together and said, okay, we need to do something about organizing our data better. But still, I started, in fact, and that was what Markus was alluding to, I started my work on atom probe in 2017, mainly on the data-centric side. And the only thing that I want to mention is, what can you measure with atom probe? In principle, you can measure even these, you can measure biological material, metals, ceramics, and isolators, thanks to an incredible amount of work by the community where this technique has matured. But when it comes to data sets and how they are curated, much has to be done. That's exactly what we wanted to work on in this project. But look also how long this time window is from where basically the community realized that there's something that we have to do, and still how much time it took then that people at least agreed upon, okay, then we should do something. And that's why we can immediately see that we cannot expect now in two or 3 days something to happen just because it's implementable. Okay. What I want to do now is, what is the motivation and aim of specifically this topic and project on atom probe tomography that Christopher's already alluded to? What specifically are we doing? And then I want to immediately jump into concrete things and tasks that we have done for the community to help solve them specific issues that are happening in the community. There's obviously a relevance seen in the FAIR data that works very nicely. And the chance that the German NFDIDs offers now is that we have, I think, here the unavailable pool of developers that can now spend time on this. And specifically in the FAIRmat project, we have this specific part of atom probe tomography where I'm the task leader together with Dirk Rabe and Baptist Gold, who stands in at the moment for basically the administrative part for Dirk. And then we have this part also with electron microscopy, because at some point these techniques will come together in the near future. But there's also this MATFRAG project where most of the work on atom probe tomography with this technique is frequently used. And that's why we here in this project in this common project between MATFRAG and FAIRmat, we decided, well, we'll make one project together where we really walk in deep detail into our tools, our software tools that we have, and try to find a way how we can, first of all, prepare the software tools in such a way that the algorithmic procedures are better documented. And once we have that, then done that, then we can take data sets from the community and really apply methods right on the same data sets, like extracting grain boundary and checking how the individual grain boundaries then look like and what the differences are. But in order to get there first, we first had to do much with the legwork and homework first, namely cleaning up our data, and that's really professionalizing software tools. So the first thing that we did was we decided, okay, we need to have a way, and we also need to work really on sharing and developing prices for atom probe tomography file formats, because most file formats in atom probe are not formally specified via computer science approaches. They're just ad hoc tables in either binary form or text form that people have come up with, and basically the community accepted them. So what we immediately decided in the project is we said, well, all of our parsers that we're developing for NOMAD, we basically bring out in a dual role. They are put in a Python library, and they are immediately brought to the community that the community can use them for whatever they want to do. But if they write now Python tools, they can use it. But also we use these tools now to parse data inside NOMAD Oasis. So then basically we call this library also inside NOMAD Oasis. And also what we've done, we collected version example files in order to basically counter this, challenge this problem of no formal specification. So basically learn how the files are organized via somewhat of a reverse engineering. And for that, I just here give the links, because everything else would, in particular, if I give the talk, would be too quickly, too technical. That is all. This open source domain. That's what we're using. It's an open source library for file format parsing. Everybody's welcome to approach. At the moment, we are focusing on Python. But there are also many parsers out there that other people could immediately put up there, and then with that help to coordinate their efforts better. The second thing that was immediately clear that we have to do is whenever you talk to atom probers, you typically get files and you get the measurement, in fact, in what atom probers often refer to as a POS file. That is nothing but a binary table with like the atomic position reconstructed, which is already an interpretation of the raw data, because you have run a computational algorithm to place the atoms from the incomplete information, because you just have the two-dimensional detector information and time of flight, and from that you have to reconstruct where atoms were. The problem is these files, or these issues, that these files typically have no contextualization inside that tells, okay, you can sell me anything as a POS file, and I wouldn't even know whether it's an data set. So that's why it's immediately clear that you need to have another vehicle and tool whereby you can collect contextualizing meta information. And that is obviously in ELN. And for that, we in fact use this so-called custom schema functionality that also saw in several talks from Christoph and Andrea and others in NOMAD, which we in fact customized with an example for customized in the sense that we prepared an example for atom probers that is very close to what they typically would find in the commercial software, so they can enter the data. So that was our suggested solution. And that looks basically as follows. You have this mask that is here configured quite extensively. Now people always ask me, is this necessary like this? Does it have to be so extensive? No. In principle, you could cut all of this out, put in a text file and load it along the parsing process. That wouldn't be a problem. But here, for the sake of explicitity, I put it this way to show that, in fact, all of the different capabilities that the custom ELN schema is capable of were very useful and can also be very useful for atom probers. And then you can either decide, okay, where were my pulsar settings and where were my instrument settings. Ideally, it would be that this would come directly from the commercial vendors. However, the problem is they're still in negotiations in the company whether they are willing to open their proprietary file formats for us. It's so simple. And I cannot tell you more about that. And that's a process that takes long, but the next opportunity will be the APDNM conference in August, where we again will meet them, and hopefully the more we ask, we get forward with this. Then we also worked on standardizing information exchange. And that goes basically to try to go away from these lacking context binary tables towards something which is in fact matching the entire concept that we developed in NOMAD. Here specifically this NeXus application definition idea, where basically you compose from various sources of information, ELN, the commercial vendor files, and ranging definition files. You put together the information into a consistent data artifact that you can either use as is, without NOMAD, without being interested in anything of what we're doing, and just share it with your colleague. And you would already be much more informed than as if you were to POS file, as if you were to share a POS file. Or you could also upload these POS files directly in NOMAD, and then that parsing routine that we've developed would start automatically in NOMAD and would create this data artifact for you in NOMAD, and you can exploit it in NOMAD. This is the solution that we decided. So we went for a standardized open exchange format that combines a data schema and an agreed upon information availability. That means basically criteria that said, okay, this piece of information should be there, this information is required, and this information, everything else is optional. And most of the fields are in fact optional because we don't want to be super restrictive. But it's also clear that when you set no rules to something, you cannot expect the software to do anything with the data set, because somebody could just upload something which is empty And what would you do with it? It's obviously useless. But there are also more subtle cases where you could prove such an algorithm wrong if you always claim we don't need to set any rules with people. It's not the way how it works, and I'm not convinced that's the way that it in our cases will work. Also, that again, we have all open, and in fact, it's already all open, but there's not much publication to this, honestly, which is quite a misfit in this. However, this modeling with NeXus is, in fact, primarily, you could call it the data schema, but thanks to the work from Shajil and Chandra, and also the team, that is now also available as an OWL file because there's a converter that interconverts automatically from NeXus to OWL. So basically, yes, that is building an ontology for atom tomography. How does this work now? So if you were a user and you have no claim about NOMAD oasis, no claim about research data management system, then it would look like this. You would have various sources of information on the left-hand side. So user-specific metadata via ELN, administrative metadata, maybe from a project that the supervisor wants you to enter, and then all these more instrument-specific stuff. And at least for keeping it, the commercial vendor files that unfortunately are proprietary and binarily not encrypted, but in a format that it's very difficult even with a hex viewer to really know and make sense out of them. What we then do, and that's all inside NOMAD, and it's a single mouse click, you just drop the file in it. If you want, you customize the ELN, customize in the sense you just enter the data that fit your experiment, obviously, and not just have to program anything. And then that gets passed through, and you will get this HDF5 NeXus artifact inside NOMAD and the capabilities. Now you might say, why do I need at all such a system? Because a company like Kameka provides already commercial software where all of these laboratory management capabilities for their instruments is perfectly implemented. And that's in fact what most people use. I'm not convinced that this is a good argument. There is some truth in this argumentation, but it's rather a question of habit. And specifically because you really have to, if you make such an argumentation, you also have to be honest to yourself. So do you really factor everything in that's a solution like a specific research data management system, like for instance, NOMAD Oasis can give you, and I'm pretty sure that is not on the card at the moment for the commercial companies, because that, yes, you also have an AP suite and commercial software, but all of that you typically don't find. Like open source sharing, customizability, ML toolkits, central installations, the capability to exchange data, which is at the moment in the process of being conceptualized and I think also getting implemented in the next couple of months and certainly maybe next year. Let's see how this works. But that's oftentimes, this lower part is oftentimes what we forget. And we shouldn't compare apples to oranges. It is important that when we make a statement, we have to make this also substantiated. But the only downside on the story is at the moment that in fact the proprietary files we ask all customers basically to upload also, that they're not lost. But because we are positively hoping that at some point Kameka will understand that they should support us in our strategy, and then maybe they will also give us some more access or maybe even a library for that, or at least explain it to us, and with that we could technically implement it. So how does this look like in NOMAD Oasis? I'm just giving you the screenshots. I could also show it later on the screen drive, but in the interest of time, I think that wouldn't be feasible. The step would be as follows. You would have the upload section where you see the click, drag and drop in files. So I did that here. Then I have in fact, that is the schema description. That's basically this entire mask that you've seen from the ELN. You can completely customize it if you want. But we give already this example so that people can jump start. And in fact, when you have this template, of course, only when you fill it, you get really something that is specific, that is unique, that is an instance. And that's in fact then also here in the archive. And you have then this NeXus data artifact, this de facto HDF5 file, at the moment technically implemented as an HDF5 file, which basically combines this together into a data artifact, which later, once you are at this stage, is interpreted by NOMAD, and then certain quantities from that data artifact are taken in this now standardized representation to feed basically search interfaces and other services that are happening inside a specific implementation of the specific research data management system, NOMAD Oasis. This is how the data then look like in Oasis. So you have on the left-hand side your data artifacts. You can have different tools that you activate, and that is basically here the standardized representation that we come up with. So you have to reconstruct the data set. That's also what's showing up in a slide from from Christoph, and you can slide them through. And then if you have these data artifacts in NOMAD, and if you were to upload more data sets, you can then take advantage of search capabilities. That is very similar to what Andrea showed, and that's also available in commercial software. But keep in mind that here you could mix this up, and maybe I take this even though that might be dangerous, but I do it now. That is in fact the UTIS machine. That's a test machine on where we're running this particular version. That's a very fresh version that we did a couple of days ago. And you see there are many other data sets that have nothing to do with isotope tomography. Yeah. So there's something very much what Christoph talked about, electron microscopy, what I've also been implementing pretty heavily in the last couple of months. But if you pick that particular one with chromium, and I know there was chromium in there, that's obviously what, well, it's not cheating, but I know it's there. I could also click elsewhere, and you would find the data set on the spot. That's a little bit boring at the moment because there's only one data set, but give me a lab, and we could install that and run this, so and you would see the same table filling up all the data sets that you have in the lab. Okay, I'll have to switch now back to my slide. And again, so I think I should also converge towards an end, and I think I'm getting there. People often ask us about interoperability. In NOMAD, at least from a historical point of view, there was always this NOMAD, and there is still this NOMAD Metainfo, which is used. And in fact, since Chandra and Theodore and Markus, they spent quite amount of time to write a generic parser to parse from NeXus internally towards NOMAD Metainfo. And then you have here an API-capable glossary of the entire terms that we came up with, the entire ontology that we have developed for atom probe tomography. Here I selected only the case that I showed you, that's the tiny portion I showed you today, but also have a look down here. There are many more application definitions, i.e. data schemas that we've developed for specific post-processing operations that people typically do in atom probe tomography. And one of which I would like to highlight, that is this one is APM composition space results. That is exactly the application definition that we're now testing out with the people from Matwerk to use it in their software tool that they're developing in Düsseldorf to show that, in fact, at least the one way to getting the data from the Düsseldorf and the Matwerk representation towards like NOMAD works. And then we now work further on this project. We, of course, will also want to map back, but I'm going to, of course, only describe what we've done. So this last slide goes exactly to what we're doing exactly in this bridge project with Matwerk is we have understood that in atom probe tomography, we need to professionalize our software tools. There's no way around that. And that means on the one hand, professionalizing the documentation, professionalizing the algorithms being used, the state in which the Git repositories are in. There are sometimes no unit tests, there's sometimes not even clear programming styles, tests, and whatever, unclear documentation, not even descriptions or whatever, not even example data sets. That is something that we change. And basically the strategy that we have approached and how we're doing this at the moment is with my background that I can deliver, and to some extent also a little bit with the B team, we are supporting now individual test users who think this is a good approach to move forward in the future, specifically the people in Leoben, now the people in Düsseldorf together with Tillmann and Thomas, as I said, and also people who are interested or who at least have claimed that they are started to getting interested, like Peter Pfeffer's group in Erlangen. And we basically at the moment do somewhat of consulting where we help them to go into the atom probe software code and not demanding them to change everything. That's not the point, but really to show them, okay, in the interest and from the perspective of the FAIR research data management principles and specifically the FAIR for research software principles that recently came out from Barker and co-workers, what steps should scientists do if they really want to claim that should be a tool that others can use? Because frequently we were running into this problem with these containerized applications that it's not about that we're not willing to put it into containers. The problem is technically that oftentimes you face the situation and the documentation of the code is not of a high enough quality that you pass this at all to automated CI pipelines, because they would directly detectable in GitHub. There's an automatism that checks, oh, well, the code is maybe doesn't check itself or some issues going up. And with that, our development stalls at this point. We cannot do anything. If it doesn't pass the pipeline in NOMAD, it's simple, it doesn't work. But it seems complicated, but in fact, if you think a little bit longer about it, it's an extremely healthy process. And I'm saying this as a testimonial here, because I started in 2017 with basically starting to write a software, Atom Probe in C++ from scratch, with starting in the same situation. And now I'm very happy that I can stand here that I had walked again over the software for the third or fourth time and doing now finally this data modeling, because with that, here, by the way, all the links that guide you to the details of the work that is behind that. I should have showed this earlier. But what we can now do with that is when we run a computer simulation and post-processing chain of, let's say you take the Atom Probe data set, you reconstruct an interface, you then get the composition profile across that interface. These codes, at least one code, and we would like to get this now working for more and more codes, starting with the people in Düsseldorf there and they open, but I think in Düsseldorf they will be a little bit quicker on that, picking this up. Point is, we would like to get to a state, as I said, I would like to go back and I don't want to ask myself, okay, what have I done 5 years ago? Which settings have I done? Because it is so difficult, in particular when you have parameterized methods, that you cannot always keep this in your brain and mind what you have done. And what is the benefit that you can get out of that? As now, all my tools, for instance, have this automated versioning and keeping track of what was the input, what was the output. We can build automated, actionable provenance, data provenance graphs. I show you here a snapshot from an instance that I created in Neo4j. It looks very technical and cryptical. Some people might fry and run away now. But what do you see here? On the right side, there are all the different tools that we're using in this software, basically where you take the data from the vendor representation, you compute the interface, you compute the distance of each atom to the interface, you maybe do a tessellation on the data set. All of these tools write version instances, and they, of course, because it's a workflow, they interconnect and reuse pieces of information and results that were coming from previous processing steps. And with that graph, typically I would have to do it manually beforehand, but now basically I have my directory where I have all these files, which in the NeXus representation, and then there's a Python script that runs over that and creates a graph automatically for me. And that is really the benefit that at the moment, I think many people are just giving away for nothing, because they try to always make the claim it's so complicated to keep track of your data. Yes, it is complicated, but the good thing is now that there are people who support this and who are also a little bit enthusiastic about this. And with that, thank you very much for giving me and the team the opportunity to present what we've been doing. Kudos here specifically to the team, to Markus and the team to building this fascinating infrastructure, Christoph for the support, Andrea for convincing me about the custom schema, which I initially was very skeptical about, but now like a lot, because I think it's one good vehicle that one can use, certainly not the exclusive solution, but one good vehicle. And with that, thank you very much for your interest and attention.